In this chapter, we will continue the analysis and design of beams subjected to bending. So, as we said, we will go over analysis and design of beams subjected to bending. We have already seen that bending will result into development of bending moment in any section of the beam. And this bending moment can be created by a certain normal stress distribution. So beams are structural members supporting loads applied at variable points along the member. And in general, they are usually straight, long, and prismatic. When we talk about prismatic beams, we mean that the cross section is not varying across the beam. Plus, if we join the centroid of each section, we will get a straight line. So this is what we mean by prismatic beam. Now, a prismatic beam can be subjected to several types of loads, including transverse loads, normal loads, etc. So in this chapter, we'll consider first beams subjected to transverse loads. Whenever we say a transverse load, this means that the force is within the cross-section plane of our, whenever you do a section, the developed force will be in the plane of the cross-section. So this is a transverse load. And in this case, the load is perpendicular to the beam, as you can see here. Now, these transverse loads can result into bending and shear forces. In fact, whenever you have transverse loads applied to a beam, if you do any cut, you will see that in equilibrium condition, in the cross section, you will have development of a shear force and a bending moment. Now, the shear force will be created by, if you want, distribution of shear. So let's say you have for each elementary area a shear force applied, and the total shear V will be calculated as integral shear stress times dA. So in overall, because of the shear stress distribution within a cross section, if you do the addition of all elementary forces, you will get the total shear in a cross section. On the other hand, for bending moment, we have learned in a previous chapter that the bending moment is created by the distribution of normal stresses, as we have seen before. So if you remember, we have the neutral axis, and we have from one side of the neutral axis, we have compression stresses. From the other side, we have tensile stresses. And then the overall distribution will create the bending moment. So already we know that bending moment is created by normal stress distribution. In next chapter, we'll see in detail how the total shear is created by a distribution of shear forces. And both shear and bending moment can be created by transverse loads. We'll learn in this chapter how to find the variation of shear and bending moment over a beam. And then based on this, we can design our beam to not exceed the maximum, the critical value of maximum normal stress and maximum shear stress that can be applied to the beam. So as we discussed, transverse loading will cause bending and shear in the beam. And we should make sure that to be on the safe side, both limits are not exceeded for normal stress and for shear stress. Now, if we have a certain angle between the force and the beam different than 90 degrees, then we will add also axial forces. Because when you have a certain angle different than 90 between the applied force and the beam, your force will be divided into two components. One along the axis of the beam, and this will cause an axial force, and which will lead to tension and compression stresses in the beam, and a transverse load that will result into bending and shear. So we'll see together that all of these can be combined in one problem. So if we have a certain inclination, if the load it has an inclination with respect to the beam. It's not perpendicular to the beam. Then we decompose it into a normal component. The normal component will lead to normal stress distribution. Okay, and already we know that the bending moment is also created by normal stress distribution. This is why we'll see after how to do superposition of all of these effects. So if we have at the same time transverse load and if you want normal load, how the total stress distribution, normal stress distribution will be. And we have the transverse load that will result into bending and shear. As we discussed, shear forces will result from distribution of shear stresses in the cross section, while bending moment is created by normal stress. So as you can see, normal stress can be the result of both normal force applied and bending moment. This is why if both transverse and normal loads are present, we need to do superposition effects that will be studied in next chapters. So in this chapter, we'll concentrate on transverse loading and how to design beams subjected to transverse loads. This is why we did together a review of statics, because drawing the shear and bending moment diagrams is essential to be able to design beams subjected to transverse loads. So as we mentioned, our objective is to do the analysis and do the design of these beams. Now, we know that beams are structural members supporting loads at various points along the member, and loads can be of different types. You can have concentrated loads. This means that the force is applied at certain points, and you can have distributed loads for which are distributed along the beam. So here the unit will be just Newton. However, for this case, we have the distributed load is in Newton per unit length, so it's in Newton per meter. And also, if you are considering 3D application, then you can consider pressure forces or distribution in pressure, and the pressure is in Newton per meter square. Now, for 2D applications, the distributed load will be expressed in Newton per unit length, so which is Newton per meter. Now, we'll see that depending on the type of loads involved, the graphs of shear and bending moment will be different. And we'll see how to deal with concentrated forces and how to deal with distributed loads. We already in the static review already have seen the different possible profiles, and now we'll use our knowledge of statics to design our beams to be able to support both shear effects and normal effects without any failure. Now, we have different types of beams, okay, and we should be familiar with statically determinate beams and statically indeterminate beams. So, for example, these are one of the most common types of beams you can face. To start with, let's say you have the simply supported beam. In the simply supported beam, you just have at the extremes a pin and a roller. And you know that the pin can develop reactions into Y and X directions. So it will prevent translation of the beam in both directions. It cannot develop a moment, okay, a moment reaction. This is why whenever you have a pin at the extremity, the bending moment will always start by 0 and will end by 0 for the roller. Now the roller can only develop a reaction perpendicular to contact with the beam. So this is the contact line with the beam. The roller can just develop a reaction that is perpendicular to this contact from roller towards the beam. And the combination of both, using both pin and roller, can ensure static equilibrium of a beam. Now another type is overhanging beam. For an overhanging beam, then the roller will not be at the extremity. You still can have a certain part. This is the overhanging part. and this is called overhanging beam. In this condition, if you want, um, if you have a force here, for example, the bending moment at the roller level will not be zero. However, when you have the roller at the extremity, if you don't put a couple, if you don't have a couple at the roller point, yani here at this point, then you can ensure that the bending moment is zero. So please pay attention. Whenever you have a simply supported beam, in case you don't have a couple, an external couple applied at the extremities, you can be sure that your bending moment will be zero at the extremities. The only case where the bending moment will not be zero at the extremities is when you put an external couple. So here, if you have an external couple, then we'll see that depending on the direction of the couple, clockwise or counterclockwise, we have a certain moment, bending moment to start with. And if we don't have it, we can be sure that at the extremity, the bending moment is zero. On the other hand, if you have an overhanging beam, if you just have a load here, this will ensure that when you do the cut, here the bending moment will not be zero. Now, we have also the cantilever beam, which is a beam fixed to at a certain extremity and free at the other extremity. We know that the fixity can develop three types of reactions. One in X. So let's say this is AX, if the point is called A. This is AY. And you have the bending moment, if you want, or what we call the moment reaction. We don't call it bending moment because bending moment is an internal moment. This is an external reaction of the fixity on the beam. So we have an external moment developed, A, and we'll see how to relate the bending moment to the reaction moment at A. Okay? So these are the types of statically determinate. When we say statically determinate, this means that by just using statics, we can solve for the unknowns. And you know that in 2D equilibrium problems, we have three equations that we can write. We can write sum of x equals 0, sum of y equals 0, and sum of moment about any point on the beam or any point on the figure is equal to 0. Now, this is not the only combination possible. You can use three moment equation, and if you need, if you use three different points, you can A, B, C on the beam. Let's say you can say that the first equation can be sum of moment about A equals 0. The second one is sum of moment about B equals 0. The third one is sum of moment about C equals 0. So you have a big variety of possibilities to write your three equations, but you cannot write more than three. If you write a fourth equation, you will have a redundant equation. So you'll not be able to find for unknowns. Maximum, you can calculate three unknowns. This is why to have a statically determinate, if you want beam, the first condition is that the number of unknowns should not be larger than 3, plus you should not have redundant supports. What do you mean by redundant supports? So for example, if you have a beam supported by 3 rollers, you cannot consider that this is a statically determinate structure, because using statics, you cannot determine what are the reactions at the 3 rollers. Because here, why we say it's a case of redundant or improper, if you want. This is improper constraint. It's true that you have 3 unknowns, but they are not properly placed because the 3 rollers can develop exactly parallel forces. So in case you have an axial load first, you cannot sustain it, no equilibrium. Plus, if you have a transverse load and you want to solve for your 3 unknowns, you will not be able, if you write 3 equations, 2 of them will be redundant. They will be, or if you want, they will be proportional to each other. So you cannot solve. Because here, the third equation, which is sum of x equals 0, will not give you anything here. Because whenever you just apply transverse load, you don't have axial forces. So already sum of x equals 0 is not used. So to get your three unknowns, you need three additional equations, and you just have two, if you want, different equations. So let's say you do sum of y equals 0, you get an equation. Sum of moments about a equals 0, you get a second. If you use a third relation, sum of moments about b equals 0, then you will see that you will have repetition or proportionality in your equations. So you cannot solve this problem. This is why we say it's statically indeterminate, because of the improper choice of your supports. Okay, so we have improper and we have redundant supports. What do we mean by redundant supports? This means that we are using more than required. So for example, here these are examples of redundant supports. If I use one pin and two rollers, then I have four unknowns. I have two unknowns at the pin, and I have this is an additional unknown for this roller, and this is an additional unknown for this one. So I have four unknowns, three equations that I can write. I cannot solve statically. I need an additional tool, and in this course, we'll develop additional tools from mechanics of materials related to the deformation of the beam that can help us into determining the external reaction of statically indeterminate beams. Okay. So this will be the objective of the last chapter in this course. Now you have also another. So this is called continuous beam, where you have one pin, two rollers. You have also that a beam that is fixed at one end, where you have a fixity, and simply supported by a roller at the other hand, at the other end. So here you can say that I have at the fixity three reactions, and I have the roller, which is the fourth one. So in total, I have four unknowns, and statically, I can just write three equations. So of course, here there is equilibrium, but we say it's statically indeterminate. I cannot determine the value of my reactions using only statics. I need to use another information, another equation to close my system. And this equation is related to mechanics of materials, because we'll see that the deformation of the beam will help us into writing a force equation to solve the system. Finally, the most complex scenarios is a beam fixed at the two ends. So you will have three unknowns from this part and three unknowns from this part. So you have to write six equations to solve for your six unknowns. Now, let us start by statically determinate beams. Okay, so for example, this is a simple problem where I just have a pin at extremity A, a roller at B. So if I know the type of loading acting on my beam, I can easily determine what is a y. Ax, of course, is 0 because you don't have any normal force acting on the system. So you can automatically say Ax is 0. So you just have the development of Ay and By. And to get Ay, By, you need two equations. So you can write, for example, sum of y equals 0 as first equation, and sum of moments about A or B as a second equation. Or also you can say, if I write sum of moments about A equals to 0, the only unknown will be By, I get By. So this will give me By. If I write sum of moments about B equals 0, the only unknown will be the moment created by Ay about B, so I can find the value of Ay. So you have the freedom to select the two equations you want, sum of moments or sum of forces. Now, once you determine your external reactions, you will be ready to draw your shear and bending moment diagram. We have already done the review together on how to draw shear and bending moment diagrams using area method. We also have another method called section. So, and we'll discuss it also in detail in this course, because sometimes we need it. In the section method, the advantage is you express the shear as a function of x and the bending moment as a function of x. So you can know at any value of x, analytically, you can determine what is Vx and what is Mx. In the area method, you can at specific, if you want points, find you can find then the value of V and M. Of course, for both cases, you can determine at any location. If you do the analysis of a certain location by section or by area, you'll be able to get the value. But the advantage of section method is that I do it once, I get a general expression, a general function, and then I can use it directly at any location. However, if I use the area method, I start by just determining points, and I draw shear and bending moment diagrams. And if I need to, after, to get at a certain point V and M, I should do some calculation to find the corresponding values of V and M. We'll discuss this. We'll see in which cases it's easier to use the section method, in which cases it's easier to use the area method. Okay, so now, in general, if we are interested at one location, at a certain location of the beam, okay, the easiest way to get V and M is to cut at point C, and then we can do the analysis of either part. So, or I can consider the left part and say that the left part is in equilibrium. So I have internal forces. The internal forces developed at C becomes external when I do a cut. Okay. And then to determine these stresses, I just consider this part and I say it should be in equilibrium. And I should respect conventions for shear and bending moment. Let us remember what are these conventions. Whenever, always V is positive in such a way that it will rotate clockwise about the extremity of the beam. Okay, so here if you do the analysis of the left part and you reject the right part, then the shear force at section C should rotate about A clockwise. This is why V is downward. And the positive convention for bending moment is that the moment is compressing the upper part of the beam. This is why when you do the analysis of the left part, the positive convention is counterclockwise. And of course, these two directions will be exactly the opposite if you do the analysis of the right part, because the conventions, if you want, will stay the same, but since you are considering the other part, then the direction of both will be reversed. This means that now if you take the right part, the end of your beam is B. So the shear to rotate clockwise about B should be up and not down. And the bending moment to compress the upper part of the beam should be clockwise and not counterclockwise. So these are the conventions of shear and bending. To consider a shear force positive, it should always rotate clockwise with respect to the end of the beam. And for the bending moment to be considered positive, it should compress the upper part. So when you study right parts, you use these directions. When you study left part, you use these ones. Then this is done to unify the sign, if you want. If I want to draw shear and bending moment diagrams, whatever the section I do the analysis for, I get the same expression of V and M. So when I draw on a graph, I get exactly the same result if I do analysis on right parts or on left parts. This is why we make a convention and we follow it. Okay. So the bending moment, as we know, will create normal stresses in the cross section, while the shear stress, the shear forces will create shearing stress. So whenever we have transverse loads, okay, and we do any section, we'll end up with a shear force, a total shear force V created by the shear stress distribution. And as we discussed, we'll determine in next chapter what is the shear stress distribution tau that will give me V. Okay, so this will be the scope of next chapter. Now, concerning the bending moment, we already know how it's created. It's created by a distribution of normal stresses that we studied in previous chapter. Now, what is the objective of this chapter? We know already how to relate the normal stress distribution to the bending moment. And for any material given, the material is characterized by maximum normal stress that can be sustained and maximum shear stress. So we should, if you want, make sure that we don't exceed the capacity of our beam. This is why we should consider critical sections. What are critical sections? Critical sections are sections corresponding to sigma maximum, which is the maximum normal stress, and the maximum shear stress. And depending on the material, okay, some materials, for example, are weaker, let's say, in sustaining normal stress than shear. So it depends on the material. We should make sure that both conditions are not exceeded. So this is why, to be on the safe side, we should make sure that the maximum bending moment will not lead to exceed the maximum normal stress, and also the maximum shear force V will not lead to exceed tau max. So this is the purpose. This is why the first step then should be to draw the shear and bending moment diagrams over the beam, to select critical sections characterized by maximum V and maximum M. And then also we'll see that depending if the section is uniform, okay, it's much easier for the analysis, because automatically the section of V max will correspond to tau max, the section of M max will correspond to sigma max. But we'll see after that if you have non-uniform sections, you should study each section separately. We'll see why. Okay, so whenever you have change in cross section, you should determine another maximum to determine what is the critical maximum between all of these sections. This idea will be more detailed in next slides. Okay. For example, we already know from previous chapter that the normal stress distribution in a section is given by minus my over r. And we have different factors affecting sigma, which are the bending moment value and also the geometry of the cross section. If you remember, we said that sigma is maximum, okay, for y max, and is the maximum distance from neutral axis, which is corresponding to c. So, and we said that we can say that sigma m is correspond to the sigma maximum is correspond to the absolute value of the bending moment times c over I, and we define a modulus S, okay, which is the section modulus equal to I over C. So as you can see here, there is two main factors affecting the value of stress, which is the value of the bending moment and the section modulus S of the beam. In case it's a uniform beam or prismatic beam, in this chapter we are considering prismatic beams. Okay, if you have a prismatic beam, this means that the cross section is uniform. So at any cut, you have same cross section, same as, but it's fine. So this parameter is not changing. This is a first advantage. This will simplify the analysis, because then we can just say that maximum stress corresponds to maximum moment over the whole beam. However, if you have change in cross section, the analysis will become more complicated. Why? Because you will have two parameters affecting the maximum stress: the bending moment and the modulus S. Okay, so then you should do analysis of this part and this part separately, determine what is maximum sigma in this section, in this part, what is the maximum sigma in this one, and then compare both to see which section is more critical. Because, for example, if you have M1 over S1, and for section 2, M2 over S2, okay? Of course, if the maximum moment takes place in the part characterized by the smallest S, then no need to do any comparison. And you can directly say already part 1 is more critical because it's containing the maximum bending moment, and it's characterized by the smallest value of the modulus S. However, in case you have, let's say, the maximum moment over the beam is in part 1, however, S2 is smaller than S1, then you cannot take an idea before doing calculation. You should calculate the ratio M1 over S1, M2 over S2, and then the maximum ratio will be the, if you want, more critical. Okay, so in this way you should make sure that your maximum sigma is not exceeding the maximum normal stress that can be sustained by the material of your beam. And of course, sometimes we might have different materials also. So if you have different materials, you should treat each material separately. So you should make sure that each material maximum value of sigma is not exceeded. Okay. Now, so as we discussed, now the strategy will be to first draw the shear and bending moment diagrams to determine at which location we have maximum bending moment and maximum shear. And if in case we have prismatic beams, so the cross section is not varying, we can directly determine what is the critical section, and we do the design based on the critical section. So the determination of the maximum normal and shearing stresses will require knowing the location of maximum internal shear force and bending moment. And the shear force and bending moment at a point are determined by passing a section through the beam and applying the equilibrium analysis on the beam portions on either side, as we discussed. And you can see here the convention for shear and bending moments that we discussed together. Okay. Now, let us start to do some examples to practice on this and refresh your memory about how to draw shear and bending moments diagrams. Okay, so this is the first problem. In this problem, you have a beam given for you, and this beam is subjected to transverse load. So to remind you, transverse load is a load perpendicular to the beam. We want to first see the variation of shear and bending moment to determine the critical section. As we discussed, since it's a uniform beam, so we don't have variation of the modulus S. So to determine the critical section and bending, we just have to determine the location of the maximum bending moment. This will give us a condition on the maximum normal stress in our beam. And of course, we have, since transverse load will also create shear if forces, shear stresses, then we should determine the location of maximum shear. And then this will help us into designing the beam, because we'll make sure that the material of the beam can support both the maximum bending moment and the maximum shear applied. So always in such problems, the strategy will be to first get the external reactions, because whenever I want to do a cut, I should know the external reactions to be able to calculate now the internal reactions developed. Okay. Of course, no need to calculate all reactions, because look, for example, here, if you want to always do analysis of the left part, then no need to calculate By. But sometimes doing the analysis of right part is easier. This is why always start by getting your external reactions at supports. What do I mean by it's easier to take the right or left part? For example, if you want to know what is happening between D and B, what is the value of the shear between D and B, or what is the bending moment between D and B? Then, of course, if you want to do a cut, then as you can see, this part doesn't include anything except the roller external reaction. Okay, so then it's much easier to do the analysis of this part instead of considering the equilibrium of the other part. So since sometimes, how on the other hand, if you want to do analysis between A and C, and let's say you do a cut here, of course, it will be easier to study the equilibrium of part one instead, which is the left part, instead of doing the analysis of whole right part. Okay. Now, as we discussed, we have two methods to use when we want to draw the shear and bending moment diagram, or area method or section method. Whenever you just want to find the maximum value of bending moment and shear, the area method is much easier. Okay, because all you have to do then is to first get your external reaction, and you can draw immediately by looking at the load. You draw V first, and then from V you deduce M. Let us do it together. So as we discussed, first calculate the external reactions. Here, as we discussed, a pin can develop forces along Y and X. Since here the only type of forces is transverse forces, so of course no AX. Okay, AX is 0 because we don't have any normal force acting on our beam. So we just have two unknowns, AY and BY. Now, as we discussed before, you have several ways to calculate AY, BY. Or you do sum of Y equals 0 as first equation, and sum of moments about any point in the figure equals 0 to get a second equation. Or the best choice here can be to do, let's say, sum of moments about B equals 0, you get AY, and sum of moments about A equals 0, you get BY. Okay. Now, let us do it. So, for example, if you want to find AY, you do sum of moments about B equals 0. Always specify a positive direction, and you are free to select the positive direction that you want. So you can say, I will consider any counterclockwise moment as positive. You just put the arrow near sum of moments, and then every moment created about B in the counterclockwise direction will be positive, and every moment created in the clockwise direction will be negative. So then if we start, we have the 60 kilonewton force. The 60 kilonewton force is creating about B a counterclockwise moment. So I can just say it's plus 60 times the distance from the force to B, which is 2 meters. The unit which we'll use is kilonewton meter. So the force is in kilonewton and the distance is in meter. Now, what about the distributed load? We know that for a distributed load, when we calculate external reactions, we can replace the distributed load by a concentrated force, and the concentrated force should pass by the centroid of this distributed load. Since it's a rectangular load, then the resultant force of the rectangular load should pass by the centroid of the rectangle. This means that because we have 2 meters from A, the distance from A to this resultant force is just 1 meter. And therefore, from B, the distance will be 1 plus 1, 2 plus 2, 4. So this distance is 4 meters. And you know that for a distributed load, the resultant force is equal to the area limited by the distributed load and the beam. So you have 30 times 2, which is 60. So your resultant force here is 60 kilonewton, and it's acting at 4 meters from B. And as you can see, if you apply the right-hand rule, it's a counterclockwise moment, so it's plus 4 times 60. And finally, you have AY. Now, we consider that AY is positive up. This is an assumption, okay? You can get, if you get a negative AY, this means that your assumption is wrong, then AY should be downward. But here, you can expect that AY is up because already the concentrated force and the distributed force both are creating counterclockwise moments about B. So for equilibrium, AY should be upward to create a clockwise moment opposing the two moments created by the distributed and the concentrated force. This is why here it's minus AY times the total distance between AY and B. which is 5 meters, so times 5 equals to 0. So this will give you the value of A1. You will do similar analysis to get now By by doing sum of moments about A. Or also, once you get By, it's easier to do to use sum of Y equals 0. Okay, because when you do sum of Y equals 0, you just have AY plus BY minus we said that the distributed load can be replaced by a resultant force of 60 kilonewton, so it's minus 60, and the concentrated force present is already minus 60, so you get that AY plus BY is 120. Replacing AY into if you want the equation, you get the value of BY. So you have several tools to calculate your external reactions. Once you have them, now you are ready to move to the construction of the shear and bending moment diagrams. Okay, and please always check your reactions, because if the reactions are wrong, everything else will be wrong. It will affect all of your results. So I advise you, after finding AY, BY, so here, for example, they use the two equations, sum of moment about B, sum of moment about A. Sum of moment about B gave them AY. Sum of moment about A gave them BY. To make sure that you didn't do any calculation error, verify the third equation. So check that sum of Y equals 0. If you get 0, then you can be sure that your reactions are right. If not, repeat to know what is your calculation error. Now we are ready to proceed. We'll look at first the graph of transverse load to determine V. And please pay attention. Never when you want to draw V, never use the diagram that is replacing distributed loads by concentrated forces. As I told you, we replace the distributed load here by a concentrated force just to calculate the external reactions, because external reactions will not change if you replace a distributed load by its equivalent concentrated force, which is here 60 kilonewton. However, there is a big change of internal forces if I have a concentrated load compared to a distributed load. The graphs of shear and bending moment will be completely different. This is why whenever you want to draw your shear and bending moment diagrams, always refer back to the initial loading type to know in which locations I have distributed loads, in which locations I have concentrated forces. So now, next step here, we'll review how to draw shear and bending moment diagrams using different methods, using shear and bend, if you want, the section method and the area method. Okay. To start with, let us remember the area method together. So, as we discussed here, we have a distributed load from A to C. So what we do in general for the area method, whenever I have a certain point first, if you have at the extremity a positive force upward, this will cause a positive jump in shear. So already we calculated that AY is 72 upward, so we can start by a value of 72 kilonewton for the shear. Now, as we move from A to K, or we can just here move from A to C. From A to C, the profile is not changing. We have a distributed load, and our distributed load is equal to W value is equal to 30 kilonewton per meter. Now keep in mind that W, if you go back to the review of statics we did together, the shear stress, okay, constitutes the slope of the distributed load W, constitutes the slope of the shear. Okay, so when W is constant, then the slope of variation of shear with X is constant. This means that the variation of V is linear. So you can say that from A to C, since W constant, this means that dv by dx is constant, so v is linear. Because also in the review we have seen that w, please just pay attention for convention of sign. If you consider w positive downward, okay, then you put dv over dx is minus w. And if you consider w positive upward, then dv by dx is plus w. So just you should take a convention and follow it. You can say that if I want to put dv by dx is minus w, this means that w is considered positive down, okay? And if you want to write dv by dx, so this will change from book to book, but just you should know that when w is downward, v will decrease, and when w is up, v will increase. Okay, so for any convention you use, you still get the same result. So for both cases, whenever you have, so if you want to just write dv by dx is plus w, then this means that you are considering w positive upward. In general, in most cases that we face, we have that the distributed load is downward, directed downward. This is why we take this convention here in this course material. We consider that dv by dx is minus w, and w is counted positive when it's downward. Okay, so now because you have w downward, this means that your shear is decreasing because you have a negative slope. Okay, and it's linear because omega is constant. So we have a linear decrease of the shear from A to C. Now to know the amount of decrease, we just can use the concept that delta V, the variation delta V between 2 points is equal to minus the area limited by omega curve, okay? Minus area between omega and the axis of the beam x. Because if you look at this figure, for example, the area between W and the beam is this area here. It's equal to the rectangular area. And this area is equal to 30 times 2 equals to 60. And this means that delta V here is minus the area, which is 60. So V will drop from 72 to 72 minus 60, which is 12. And it will variate linearly from A to C. Okay? So in summary, you just have to determine 2 points. V at A, which is equal to the reaction at A, which is plus 72. Now, we just have to know what is V at C. V at C is V at A minus 60 because the change in V is equal to minus the area limited by omega and the axis. So it's VA minus 60, it's equal to 12. And then because you know that it's a linear variation, all you have to do is to join the 2 points to get the variation of V between A and C. Now, to continue, from C to D, there is no transverse load applied. You don't have any force applied between C and D. That's why the shear will not vary between C and D. It will keep a constant. You can consider simply that omega is 0 here. So dV by dx is 0. The shear is not changing. It will maintain a value of 12 between C and D. Now at D, we have a downward concentrated force. A downward concentrated force, when you are moving in your shear diagram from left to right, okay? So I started by A and I'm going towards B. I'm moving from left to right. A downward force will cause a downward jump in shear, okay? So here, and this downward jump is equal in magnitude to the value of the force. So since you have a force that is downward equal to 60 Newton, then the shear will drop downward by a value of 60 Newton at point D. So it's a sudden drop in shear. And since the shear was equal to 12 and it should drop 60, then of course, just after D, the value will be minus 48. So if you want, we call, this is point D. We call the point just before D minus and the point just after D plus. Okay. So we have a sudden jump at D from 12 to 12 minus 60, which is equal to minus 48. And now from D to B, if you go back to the figure also, to the load, to the transverse load figure, you don't have any force between D and B. So your shear will be maintained constant until reaching B. To verify your result, to verify that you didn't do any calculation error or that your reactions are fine and your shear diagram is fine, make sure that this value here is equal to minus By. And why you should verify this? Because just after By, what will happen? Just after By, you don't have anything. Yani you should go back to zero. And what will make you go back to zero is an upward reaction. And this upward reaction is the reaction at B. The reaction at B should be equal to plus 48 to bring you back to zero. Because if you do the analysis of shear, what is shear? If you do just a cut here just after B, you don't have anything. Just after here, don't have anything. So sum of forces to be zero, you don't have shear value. Just after B or B plus should be zero. And just before B, B minus should be equal to minus the reaction at B. And that's why you can verify if you want in this way that your calculation is right. Okay. So always at B minus, just before reaching B, the shear force should be equal to minus By. So if By is positive upward, so if By is upward, then you should end up by a negative shear value at B. And if By is negative, then you should end your shear diagram by a positive value because the reaction will bring you back to zero. So this is for the area method to draw the shear diagram. Now, another method is the section method, which is used in this problem here. If you want to use the section method, then you will develop for any position x between A and C, what is the equation of shear? And how you decide on how many sections you should do, simply you should consider in which parts I have change in type of load. What I mean by this, from A to C, the type of load is the same. It's distributed load. So I can just do one general section, I call it section 1, and I express in this zone the shear function of x, where x represents the distance from A to the section. Okay? And then x will vary from 0 to 2, because from 0 to 2, I have the type of load is not changing. Okay? And then for any, I can replace x by any value from 0 to 2 to get the corresponding shear. And the idea will be to consider a section. Once I consider a section, or I do the analysis of the left part, or I do the analysis of the right part, I select the easiest one. Okay? Of course, here the easiest part for a certain cut x will be this one, because in this part, the other part will have distributed load and you will have concentrated force, so you have much more loads to take into consideration. Of course, you will get exactly same result. Whatever is the section you take, right or left, you will get the same expression of V. But you select the easiest part. We'll see after that, for example, when we do another section here, then of course it's easier to deal with this part. Okay, so now we start with the first section. The first section, as we discussed, just let us see how many sections we need before proceeding with each section separately. As we said in the, and again, keep in mind to determine what are the sections you need. You never work with, if you want transformation of distributed load into one resultant force. because as we discussed, the shear and bending moment will completely change if you replace a distributed load by a concentrated force. You can only do the replacement when you are calculating external reaction, or when, if you want, your section is not passing by the distributed load. And for example, if I'm doing a section after C and I want to do the analysis of internal forces between C and D, I can replace the distributed load here by one resultant force, because then it's similar to getting external reactions. Okay, because the section is not passing by this part, and I can say that the effect of this part on forces, when I study external forces and do sum of y equals 0, sum of moment equals 0 to find forces at this section, I can replace the distributed load by a concentrated force. But when I'm studying in any part here between A and C what is happening, I cannot say I will replace the distributed load by a concentrated force, because look, if you just do the comparison, if you replace your distributed load by one resultant force, and then you look at what is changing between A and K, then you will say nothing is changing here. So V should remain constant between these two. While actually it's not the case. V is varying linearly from A to C. If you replace your distributed load by a concentrated force and you draw the variation from A to C, you'll get this. You'll get, I have 72 first. I have a drop of 60 suddenly at K, which is at center between A and C. And I maintain from K to C a value of 12. And this is completely different from the actual behavior, which is linear variation from A to C. So always keep in mind, whenever you have distributed load, you first determine the sections. You do the section. Whenever a section is passing by a distributed load, you cannot replace it before doing the cut. After you do the cut, so here, for example, after you do the cut, you can say, to study the value of V and M, I can replace this distributed load by one concentrated force, because now it's like I'm calculating external reactions, because when I do the cut, internal forces becomes external. And the value of V and M will not vary if you consider a concentrated force replacing the distributed load then, after you do the cut. So, to summarize then, the first step in section method is to determine how many sections do we need. Okay, so if I consider the following figure, first I need section 1 between any point between A and C. Now from C to D, if you have, I don't have anything, so I need one section from C to D. Whenever you have a new load, you need a new section. And at D, I have a concentrated force. This means that I need a section before D and a section after D. So the third section is between D and D. So in total here, if I want to use the section method, I need to do 3 sections. One between A and C, one between C and D, and one between D and D. Okay. Once I determine the number of sections needed, I move to getting the equations of V and M in each of these sections. So to start with, I can do section 1. When I do section 1, as we discussed, the easier part to do the analysis of is the left part. So I reject the right part, and then I say this part, the right part, should be in equilibrium. And I want to determine what should be the shear force, the total shear force, and the total bending moment developed in this section to have equilibrium of this part. So all I need to do then is to apply on this part sum of y equals 0 to get V, and sum of moment about, you can take any point of the section, but the easiest one will be to take the section point here. Why? Because in case you did calculation error for V, this will not affect the bending moment value. However, if you decide to take sum of moments about A equals 0, then the shear force will have a moment about A. And if you did a calculation error in V, this will lead to a calculation error in M. This is why it's advised always to take sum of moments about the point of the section to reduce the possible error. Okay, and always you can verify at the end if your result is logical or not by saying that to have right result, we know that dv by dx, the derivative of shear, should be, so if we derive, if you derive m dm by dx, you should get the shear. Okay, so we'll see together that the shear, we already have seen this in the review, the shear is the derivative of bending moment. So when shear is positive, bending moment is increasing. When shear is negative, bending moment is decreasing. So you can use this to verify that your equations are right. So let us do this together. So first, as we said, whenever we use the section method, then we are considering any location x between a and c, and we'll express v and m both function of x. Okay. To start with v, I want to get what is v. I do sum of y equals 0 on the left part. What do I have? I have the reaction at a, of course. It's I consider sum of y positive up. So always put the convention you are taking near your formula. I have plus 72, and we know that shear is considered positive when it's rotating clockwise about the end of the beam. So since I kept the left part, then V is considered positive downward. This is why I put V downward. And when I do sum of y equals 0, because my positive convention is up, I just put minus V. And now this distributed load is equivalent to a resultant force equal to the area of the rectangle. And the area of the rectangle is the height, which is 30, times the width, times the length, which is x. So 30 times x. And since it's downward, so it's minus 30 times x. So I deduce that in section 1, V is given by 72 minus 30x, which is a linear decreasing function. So as expected using the area method, I have a linear decrease in first section. And now all I have to do to draw my graph is to take 2 points. So if you replace for x equals 0, you get 72. And for x equal to 2, you get 72 minus 60, which is 12. So you obtained exactly same result of area method. Now, in order to determine the bending moment in this section, function of x, I do, as we discussed, I do sum of moment about this point equal to 0. And I take a positive convention. I consider, let's say, the positive convention is counterclockwise. Already, my bending moment is positive when compressing the upper part of the beam. So because I considered the left part, then the bending moment is positive when it is counterclockwise. This is why I put here plus m first. Now, this force is creating a clockwise about the section point. So I have minus 72 times this distance, which is x. Now, in order to account for the moment of the distributed load, I say that the distributed load can be replaced. And after I do the cut, as I told you, I can replace the distributed load by an equivalent force. This equivalent force in A is equal in magnitude to the area of the rectangle, which is 30 times x. And it should pass by the centroid of the rectangle, which is at x over 2 from the extremity. So the distance from the concentrated load, replacing the distributed load to the section point, is x over 2. This is why I multiplied 30x times x over 2. And as you can see, the moment created is counterclockwise about this point. This is why it's plus 30x squared over 2. And then in total, I get that the bending moment at any x location within section 1 is 72 minus 15x squared. As I told you, to verify your result, derive m. If you derive m with respect to x, here you have 72, x is missing here, okay? It's here. So if you derive m, you get dm by dx is equal to 72 minus 30x. So you can verify that it's right. This is V. Okay. And now to draw the bending moment, you can say I have a parabolic variation of the bending moment in this region. And then you can take, if you want, 3, 4 points, and you can draw it easily. You take x equals 0, x equals 1, x equals 2. You can draw. Okay. Now, if you want to continue with the section method, now we take the second section. The second section is between C and D, as we discussed before. So going back to this figure, this is our second section. Now, when you do the second section, the easiest part to do the analysis of is this one. Okay, because then you don't have any more a distributed load. Or if you want also, both are relatively simple, because we said that whenever the section is not passing by the distributed load, I can replace the distributed load here by 60 kilonewton. So the two sections, right and left, are nearly equivalent. You can take whatever you want. Okay. So feel free to take the analysis of the left part or right part. It doesn't matter. When it doesn't matter, take the left part. So this distance is x. Because if you want to take the right part, you should pay attention to express this length always function of x. So it will be the total length minus x. Okay, because don't change origin. We don't change origin because we are at the end we want to plot our graph with respect to the same origin of x. Okay, you can do change of origin. It's not wrong, but it will complicate things, because you should pay attention when you draw the final graph to locate back with respect to one origin, which is A. Okay, so from beginning, when you do your cuts, always use A as origin. So x represents the distance from A to the cut. So if you keep the right part, then this distance will be the total length of the beam minus x. We'll do it in the last section, because of course in the last section it's much easier to keep the right part and reject the left part. So now, as we discussed, when you do the cut here, you can replace the distributed load by a concentrated force of 60 kilonewton acting at 1 meter from A. And then you will have a very simple part to do the analysis of. You just say, when I do a cut here, the positive convention for V is down, the bending moment is counterclockwise, and to find V and M function of X, I just apply sum of Y equals 0 and sum of moment about this point, which is any point between C and D equals 0, where the distance from A to that point is X. And of course, second section is valid for X varying from 2 to 3. Okay, so now I say I want to find the equations for X varying from 2 to 3. Sorry. So I put the figure, and I say, let me do the analysis of this figure. Then all I have to do is to apply the equilibrium equation on this part. So here, as you can see, this is the first section. This is the second one, from C to D, from 2 to 3 meters. We can replace, as we discussed, this by distributed load by a concentrated force. And now to get what is V, okay, we say that sum of forces along Y equals to 0. Now, what are the forces acting on the left part, which is remaining? We have the 60 kilonewton, which is the equivalent force of the distributed load. We have, of course, the reaction at A, which is upward. So you have plus 72 minus 60 and minus V, because as we said, V is positive downward. So it's minus V equals to 0. So you can deduce, as expected, that between 2 and 3, the shear is constant, because nothing is changing. You don't have any load change from C to D. This is why you can expect that V will be constant, and V value will be equal to 72 minus 60 equal to 12. And we verified then the result obtained by the area method. Now, if you want to find the expression of the bending moment, then we apply sum of moments about this point is equal to 0. Already you have the moment of the reaction at A. This moment is, using the right hand rule, is clockwise. So since we consider the counterclockwise as positive, so you put minus 72 times the whole distance here, which is x. So as we said, x represents the distance from the origin to the section. So this is x. Now, to determine the moment of the equivalent force to the distributed load, which is 60 kilonewton, we need to express the distance from this force to the end point here of the section, function of x. We know that from A to the centroid of the distributed load, you have 2/2, which is 1 meter. This means that the remaining distance from the equivalent force of 60 kilonewton to the section point is the total distance x minus 1. So this is x minus 1. And since you have a counterclockwise moment created by this equivalent force, you put plus 30 times 2, which is 60, the equivalent force, times this distance, which is x minus 1. And finally, don't forget, of course, the bending moment, which is here in the positive direction. So plus m equals to 0. And then you get that m is equal to 12x plus 60. As usual, to verify, if you derive m, you will get v. If you derive this equation, you get 12. So this is v. So you can verify that the derivative of m is equal to v. Now, concerning how to verify your constants, first here, there is no jump in bending moment. The only source of jump in bending moment is a couple, is when you have a couple. And we'll see, let's say, if I have a concentrated couple in the beam, then at the point of where I have the concentrated couple, I will have a jump in bending moment. And for the shear force, the only source of jump is the concentrated force. So whenever you have a concentrated force on your beam, you will have jump in shear. Whenever you have a concentrated couple on your beam, you will have jump in bending moment. And here, since you don't have any concentrated couple on your beam, then you can expect that I have no jump in bending moment. And this can be helpful for you to verify your results, because from previous section, okay, from section 1, you can calculate at x equal to what is the bending moment at point C. Because there is no jump in bending moment, so if you replace x by 2 in section 1, and you replace x by 2 in section 2, you should get exactly the same result, because the moment is continuous here. And we can verify this, okay? If you go back to your previous expression here, when you replace x by 2, you will get 72. Here, don't forget, we have a typing error. We should put here 2. So you have already 72 times 2 minus 15 times 4. Okay, so you get 144 minus 60. Okay, so you should have a bending moment of 84 at x equal to 2. Let us verify that we have obtained the same result using now x equal to in the second equation. So in section 2, we got the expression of bending moment is 12x plus 60. If you replace x by 2 here, you'll obtain exactly the same result. Okay, so 12 times 2 is 24, plus 60 it's 84. So everything is going well. I have continuity and bending moment as expected. Okay, and now between C and D, the variation of bending moment will change. In section 1, it was parabolic. Why? Because V was linear, and V is the derivative of M. So when V is linear, M is parabolic, while between C and D, V is constant. So when V is constant, M becomes linear. So what will change is the profile. The moment is continuous, but will change in profile between section 1 and section 2. It will move from parabolic profile to linear profile. Okay? And finally, I have now the third section to do. My final section will be for the part from 3 to 5. Okay, the total length of my beam is 5 meters. So I will do a third section from C to B. And as we discussed, for the last section, of course, it's easier to keep the right part. So I will keep the right part, and just I keep in mind, I will not change my origin. My origin is always A. And since the distance from A to the section is X, then the remaining part will have as length the total length of the beam, which is 5 meters, minus X. So this distance is 5 minus X. Now, because I kept the right part, the V and M will be reversed. So V is considered positive, as we discussed, when it's rotating clockwise about the end of the beam. So now V is positive upward, and the bending moment is positive if it's compressing the upper part of the beam. So here the bending moment is positive when clockwise. Now to get the values of V and M, all I have to do then is first to say sum of y equals to 0. So I have to do plus V plus 48 equals 0. This will give me V equal minus 48. So my shear is negative for the last section. And as expected, V is constant for last section because I don't have any variation from point C to B. Okay, so because I don't have any variation, then if you go back to the figure here, just the one of the load here, sorry, from D to B I mean. Okay, so from D to B, when you do the last section, you don't have any load variation from D to B. So you expect that the shear will not vary from D to B, which is not the case between A and C. Between A and C, you have a distributed load. You will have a continuous change in shear. However, from C to D, nothing is changing, so no change. Just at D, I have a concentrated force, so I have a downward jump. And after D, I will maintain a constant value. And this is, again, clear from the section method. From the section method, I will get constant value. And I can verify that this constant value is minus By, as we discussed before. Because By is plus 48, and I got that V is minus 48. Now, to get the bending moment, all I need to do is sum of moment about this point equal to 0. And considering the equation positive direction is counterclockwise, so since the moment here is clockwise, I just put minus M. And the shear is creating a counter-clockwise moment about this point, so it's plus the reaction force, which is 48, times this distance, which is 5 minus x, equals to 0. And please keep in mind here, it doesn't matter what is the convention you choose. You can say I will consider the clockwise as positive. All what will change is here that you say then I have plus m and minus 48 times 5 minus x equals to 0. So the selection of positive direction for your equation will not affect your result, okay? Because all your terms will be just the opposite. But keep in mind that the bending moment is considered positive when compressing the upper part. So you should put the bending moment here positive clockwise. If you put it counterclockwise, you'll get a wrong result, okay? So always the positive convention of your bending moment is in a way that it's compressing the upper part of the beam. So now we can also verify again that if I derive the expression of bending moment, I will get B. Okay, and since V is linear, since V is constant, M is linear, and since V is negative, M will be decreasing. And you can verify this again from your graph. So now in the section method, once you have all your equations, you can just plot the variation. But of course, you can see that the area method is faster, unless after sometimes we need the equation. When you need the equation function of x, of course, you need the section method. But when you just want to have your graphs of V and M to determine, let's say, the maximum shear, the maximum bending moment, it's easier to use the area method. Okay, and now as usual, also a verification will be to verify continuity of the bending moment. Here the continuity at Cx equal to sorry, at Dx equal to 3. So if you replace x by 3 here, you get 240 minus 48 times 3. You can verify that you get the same result if you replace in the previous equation x by 3, which is 12 times 3 plus 16. Both will give you the bending moment at point D, which is 96. Okay, and now going back to the area method, let us see that it's much easier to deduce the profile of M using area method. If I want to use now, instead of section method, the area method to get the bending moment, then all I have to do is to look at the graph of shear, and from the graph of shear, I will deduce the graph of the bending moment. Now, please keep in mind, when you want to draw by the area method, if you want bending moment diagrams, you should not only look at shear, you should also look at the beam to see if you have any couple. Because as we discussed, the couple will lead to a jump in bending moment, and we cannot see it on the shear diagram. So always you should take a look at, if you want, the load on the beam and the shear diagram. If you don't have couples, it's fine. No need to look at your type of load. Okay, you can just rely on the shear diagram. But in case we have couples, and we'll do some examples with this, the presence of couples will lead to discontinuity in bending moment. So this is why we should look at the beam to see at what locations we have these concentrated couples. Now here, since we don't have the case, we just can look at V function of x. And of course, by just looking at our type of load, we can say that because we have a simply supported beam and we don't have any couple, so we should start by bending moment 0 at A, and we should end by bending moment 0 at B. So these are verifications for us. At B, you should verify that you should end by 0, and of course at A you will start from 0. Now, we start from 0 because we don't have any couple at A, and then to continue, we say, let us see what is happening in the shear diagram from A to C. From A to C, I have V is linear, positive, okay? And since V represents the slope of M, if V is linear, then M is second degree parabola. So you can automatically say that here I have a second degree parabola. And since V is positive, then M is increasing. And because V represents the slope of M, I can say that I started from 0. The slope here at 0 was 72. So it was a high slope. Now, since V is decreasing gradually, the slope will decrease. This will give me a downward concavity for the bending moment. And also you can verify that I have downward concavity because since V represents the first derivative of M, the second derivative of M is minus W, okay? And since here W is downward, and here we consider the convention that W downward is positive, okay? So the second derivative of M is minus W is negative. So we have a downward concavity of bending moment. And we can verify this from the decrease of slope. V is decreasing, this means that the slope is decreasing, and this will give me a downward concavity. Now, to determine what is the value, this will stop here at C, of course. I will stop the second degree parabola at C, And to know what is the value of the bending moment at C using the area method, I say that the variation of bending moment from 0, which is from A to C, is just equal to the area under this curve.